Generate local keys using the node template. You have already used the some command line options to start your local blockchain node using the predefined Alice and Bob accounts. You can also use command line options to generate random keys to use with Substrate. For this tutorial, you can remain connected to the internet and use your local node to generate your keys. As our best practice, you should use an air-gapped computer that has never been connected to the internet when you generate keys for a production blockchain. At a minimum, you should disconnect from the internet before you generate any keys you intend to use on a public blockchain. As our best practice, you should use an air-gapped computer that has never been connected to the internet when you generate keys for a production blockchain. At a minimum, you should disconnect from the internet before you generate any keys you intend to use on a public blockchain. To generate keys using the node template, open the terminal shell on your computer. Change to the root directory where you compiled the Substrate node template. Generate a random secret phrase and keys by running the following command. Type a password for the generated keys. The command generates keys and displays output similar to the following. You now have the ESA 25519 key for producing blocks using Aura for one node. In this example, the ESA 25519 public key for the account is Use the secret seed for the account you just generated to derive keys using the ED 25519 signature scheme by running the following command. You now have the ED 25519 key for finalizing blocks using Grandpa for one node. In this example, the ED 25519 public key for the account is 5 CuxCGFWQHJGZS5MNQ36TB651mu9G8XQ4JIU of PCJVM. Generate a second set of keys. For this tutorial, the private network consists of just 2 nodes, so you need 2 sets of keys. You have a few options to continue the tutorial. You can use the keys for 1 or 2 of the predefined accounts. You can repeat the steps in the previous section using a different identity on another computer to generate a second key pair. You can recruit other participants to generate the keys required to join your private network. For illustration purposes, the second set of keys used in this tutorial are ESA 25519, 5HJ232J2V7B9EHF47JNT44BFAPWIC BWEI6 for Aura, ED 25519. 5 FEJX from JLTH1 VBXZT5KHVJ84Z5LK7NU87GZS for Grandpa. Create a custom chain specification. After you generate the keys to use with your blockchain, you are ready to create a custom chain specification using those key pairs. Then share your custom chain specification with trusted network participants called validators. To enable others to participate in your blockchain network, you should ensure that they generate their own keys. If other participants have generated their key pairs, you can create a custom chain specification to replace the local chain specification that you used previously. This tutorial illustrates how to create a 2-node network. You can follow the same steps to add more nodes to your network. Modify an existing chain specification. Previously, you added nodes to the blockchain using the predefined local chain specification using the chain local command line option. Instead of writing a completely new chain specification, you can modify the one that you have used before. To create a new chain specification based on an existing specification, open a terminal shell on your computer. Change to the root directory where you compiled the substrate node template. Export the local chain specification to a file named custom.spec.json by running the following command. Export the local chain specification to a file named custom.spec.json by running the following command. If you open the custom.spec.json file in a text editor, you would see that it contains several fields, including a large blob that contains the WASM binary for the runtime you built using the cargo build release command. Instead of viewing the entire file, you can preview the first and last few lines to see the fields you need to change. Preview the first few fields in the custom.spec.json file by running the following command. Preview the last fields in the custom.spec.json file by running the following command. This command displays the last sections following the WASM binary field, including the details for several of the palettes, such as the sudo and balances palettes, that are used in the runtime. Modify the name field to identify this chain specification as a custom chain specification, for example. Modify or field to specify the nodes with the authority to create blocks by adding the ESA25519 SS58 address keys for each network participant. Modify the grandpa field to specify the nodes with the authority to finalize blocks by adding the ED25519 SS58 address keys for each network participant. Note that there are two data values for the authorities field in the grandpa section. The first value is the address key. The second value is used to support weighted votes. In this example, each validator has a weight of 1 vote. Save your changes and close the file. As you have just seen, you can add and change the authority addresses in a chain specification by modifying the OR and GRAMPAR sections. You can use this technique to add as many validators as you like. To add validators, modify the OR section to include ESA 25,519 addresses. Modify the GRAMPAR section to include ED 25,519 addresses and a voting weight. Be sure to use unique keys for each validator. If two validators have the same keys, they produce conflicting blocks. For additional information about working with key pairs and signatures, see public key cryptography. Convert the chain specification to use the raw format. After you prepare a chain specification with the information you want to use, you must convert it into a raw specification before it can be used. The raw chain specification includes the same information as the unconverted specification. However, the raw chain specification also contains encoded storage keys that the node uses to reference the data in its local storage. Distributing a raw chain specification ensures that each node stores the data using the proper storage keys. To convert a chain specification to use the raw format. Open the terminal shell on your computer. Change to the root directory where you compiled the substrate node template. Convert the custom spec JSON chain specification to the raw format with the file name custom spec JSON by running the following command. Share the chain specification with others. If you are creating a private blockchain network to share with other participants, ensure that only one person creates the chain specification and shares the resulting raw version of that specification. For example, the custom spec JSON file, with all of the other validators in the network. Because the Rust compiler produces optimized WebAssembly binaries that aren't deterministically reproducible, each person who generates the WASM runtime produces a slightly different WASM blob. To ensure determinism, all participants in the blockchain network must use exactly the same raw chain specification file. For more information about this issue, see hunting down a non-determinism bug in our Rust WASM build. We recently learned that the WebAssembly build in our system isn't deterministic any longer. This is a short summary of what we did to chase down the bug in the hope that this helps others facing similar issues, give some help and guidance on what to try or how this kind of thing works. A bit of background: Substrate, our stack at Parity. We are building software to run the next generation of the web, a trustless secure web 3.0. Most notably, we are building the Polkadot network based on Substrate. Substrate is natively compatible with Polkadot, thus making it simple to secure your blockchain and communicate with Polkadot's network. We have built everything using Rust, which means no legacy codebase, and it's open source. Launch the private network. After you distribute the custom chain specification to all network participants, you're ready to launch your own private blockchain. The steps are similar to the steps you followed in Start the Blockchain using predefined accounts. To continue with this part of the tutorial, you are no longer using a single physical computer or a single binary. To continue, verify the following. You have generated or collected the account keys for at least 2 authority accounts. You have updated your custom chain specification to include the keys for block production, Aura, and block finalization, Grandpa. You have converted your custom chain specification to raw format and distributed the raw chain specification to the nodes participating in the private network. If you have completed these steps, you are ready to start the first node in the private blockchain. Block production, Aura, and block finalization, Grandpa. Substrate supports pluggable consensus, so a developer can choose from among several consensus algorithms. It comes standard with 4 algorithms. Some of these, Egg Babe and Grandpa, can even be used together in a single node. What are the differences between each consensus algorithm, and which ones can or should be used together? For a blockchain to be live, continue growing and adding new transactions, 2 things must happen to solve the problem of distributed consensus. Typically, these jobs are performed by full nodes, as is the case with the default Substrate node. Block authoring. Nodes create new blocks. Each new block contains a reference to a parent block. Block finalization. When forks appear in the chain, nodes must choose which side of the fork to consider the real or canonical one. Once a block is finalized, the canonical chain will always contain it. Let's look at each of the algorithms mentioned individually, and see how they accomplish those tasks. Block authoring. Aura. Aura primarily provides block authoring. In Aura, a known set of authorities are allowed to produce blocks. The authorities must be chosen before block production begins, and all authorities must know the entire authority set. Time is divided up into slots of a fixed length. During each slot, one block is produced, and the authorities take turns producing blocks in order forever. In Aura, forks only happen when it takes longer than the slot duration for a block to traverse the network. Thus, forks are uncommon in good network conditions. Babe also primarily provides block authoring. Like Aura, it is a slot-based consensus algorithm with a known set of validators. In addition, each validator is assigned a weight which must be assigned before block production begins. Unlike Aura, the authorities don't take turns in order. Instead, during each round, each authority generates a pseudo-random number using a VRF. If the random number is lower than their weight, they are allowed to produce a block. Because multiple validators may be able to produce a block during the same slot, forks are more common in Babe than they are in Aura, and are common even in good network conditions. Substrate's implementation of Babe also has a fallback mechanism for when no authorities are chosen in a given slot. Proof of work. Proof of work also provides block authoring. Unlike Babe and Aura, it is not slot-based, and does not have a known authority set. In proof of work, anyone can produce a block at any time, so long as they can solve a computationally challenging problem, typically a hash preimage search. The difficulty of this problem can be tuned to provide a statistical target block time. Block finalization. Probabilistic methods. Each of the block authoring mechanisms we've discussed previously needs to know where on the chain it should build the next block. Methods such as the longest chain rule, heaviest observed subtree often work in practice and provide probabilistic finality. That is, with each new block that is added to a chain, the probability that it will be reverted decreases, approaching zero. When true certainty that a block is final is desired, a more sophisticated game can be used. Grandpa provides block finalization. It has a known weighted authority set like Babe. However, Grandpa does not author blocks, it just listens to gossip about blocks that have been produced by some authoring engine like the three discussed above. Each authority participates in 2 rounds of voting on blocks. The details of the voting are beyond the scope of this post. Once 2/3 of the Grandpa authorities have voted for a particular block, it is considered finalized. Hybrid consensus. In general, a block authoring engine and a finality gadget can be used together in a single chain, as Babe and Grandpa are in the code linked in the question. When such a system is used, block authoring engines must be made aware of blocks that are finalized so that they don't waste time building on top of blocks that will never be in the canonical chain. Note on weights. Babe, Grandpa, and many other algorithms that do not come bundled with substrate rely on weights. Consensus algorithms themselves typically do not dictate how the weights are assigned, but rather assume that they are assigned somehow, leaving the assignment to an external mechanism. In public networks, it is common to assign weights based on how many tokens are staked. In the default substrate node, all weights are set to 1 because the Fragment algorithm keeps all validators close to equally staked. start the first node. As the first participant in the private blockchain network, you are responsible for starting the first node, called the boot node. To start the first node, open the terminal shell on your computer. Change to the root directory where you compiled the substrate node template. Purge old chain data, if needed, by running the following command. Note the following changes to the command you are running to start the node. Instead of the predefined Alice account, you are using your own keys. You'll add your keys to the key store in a separate step. The chain command line option specifies the custom chain specification. The name command line option enables you to give your node a human readable name in the telemetry UI. The RPC methods and safe command line option allows you to continue the tutorial using an unsafe communication mode because your blockchain is not being used in a production setting. Add keys to the key store. After you start the first node, no blocks are yet produced. The next step is to add 2 types of keys to the key store for each node in the network. For each node, add the Aura authority keys to enable block production. Add the Grandpa authority keys to enable block finalization. There are several ways you can insert keys into the key store. For this tutorial, you can use the key sub command to insert locally generated secret keys. To insert keys into the key store, open the terminal shell on your computer. Change to the root directory where you compiled the substrate node template. Insert the Aura secret key generated from the key sub command by running a command similar to the following. This example uses the secret seed generated from the key sub command into the key store. In this tutorial, the secret seed generated was 0x500 So the sorry command line option specifies that string to insert the key into the key store. You can also insert a key from a specified file location. For information about the command line options available, run the following command. Insert the Grandpa secret key generated from the key sub command by running a command similar to the following. Verify that your keys are in the key store for node 01 by running the following command. Enable other participants to join. You can now allow other validators to join the network using the root nodes and validator command line options to add a second validator to the private network. Open the terminal shell on a second computer. Change to the root directory where you compiled the substrate node template. Purge old chain data, if needed, by running the following command. Next steps. You have now seen how you can start a private blockchain with trusted participants. In this tutorial you learned how to start and stop peer blockchain nodes, how to generate your own secret key pairs, how to create a custom chain specification that uses the keys you generated, how to add validators to a private network that uses your custom chain specification. To learn more about the topics introduced in this tutorial, see the following sections. Executor for more information about the WebAssembly runtime that is a core component of the chain specification. Accounts and key management for more information about key generation and storage options. Cryptography for more information about the signature schemes used for different keys.